In this problem, we have a circuit and we also have a triangular wave voltage source applied to it. Now, we've worked with some problems that are similar to this before, maybe just like one. Actually, I think it's only been one problem that's like this before, and that's in the playlist link below the like button. But now we're going to look at this, and we need to find the steady state power over the 20 kilo ohm resistor. We need to find the average steady state power. And there's two things that are important about this. We have it over this specific resistor, and we have the steady state operation. Now, there's going to be three different kind of steps or parts to this problem. The first, we need to use our knowledge of the triangular wave voltage to find the Fourier series. Then we're going to use the Fourier series, kind of plug it into our node voltage method, and we are going to use this as like the V of G, and we're going to solve for our power. And solving for the power will be in the third part when we combine all of it together. So part one, we're going to be dealing with Fourier series, so this part right here. Now, if we didn't have to find the steady state power, it'll be in the next problem, but we won't have to do this much work. So this is a little bit more work. So when looking at this wave, we can see that the period is from 0 to 2 pi, right? And so that means that it's an even function, because if we cut this in half, and if we were to rotate this around our y-axis that we've just split, it's the same thing. So if we look at the notes linked below the like button on about page 144, we have if a function is even, what we can use. And so we're going to use this. To find our Fourier series, or to make our Fourier series, we need to use our knowledge and get AV, AN, and BN. So our AV is going to be equal to, and then we're going to have 2 over our period, and then we're running this from 0 to t over 2. And then we need to plug in our function here. Our function is just 50 times 10 to the 6th times t divided by pi times dt. Now we need to integrate this. So let's bring out everything that's constant out front. We're going to have a 100 times 10 to the 6th, and then we're going to have a t and then a pi on the bottom. And then when we integrate our t, it's going to become a t squared over 2. We can factor out the 2, so the 2 is just going to come out here. And then we're going to multiplying this basically, if we plug everything in, by t over, oh, sorry, not 2. We've already put the 2 in. It should be t squared because we've integrated. So the integration is going to give us t squared over 2. Now we need to plug in our values, so we would have our limits like this. We know that 0, if we plug it in, is just going to be minus 0. So we're not going to look at that, and we're just going to focus on the t over 2. So inside of here, I'm going to plug in a t squared over 4. And the reason why I'm skipping steps is because this is pretty simple differential equation stuff. And now from here, we can simplify this t. And now we need to plug in our t. Well, t, we know, is just shorthand for period. And our period goes from 0 to 2 pi. So we're going to have this 2 pi. We need to note that we use microseconds here. So we're going to have 10 to the negative 6th. It stands for micro. So we're going to have 2 pi and then 10 to the negative 6th. Now, this 10 to the 6th and this 10 to the negative 6 are going to cancel out. This pi and this 2 are going to cancel out with this pi and this 2. The 4 is going to make the 100 simplify, and we're going to get 25. And so that means that our AV is equal to 25. So we found our AV. Now we need to find our A of n. Our A of n is equal to, we have 4 over t. We're integrating from 0 to t over 2. So we are going to have our function 50 times 10 to the 6th times t divided by our pi. This is being multiplied by the cosine of our n. And if you're using k, because they're interchangeable, it doesn't matter. Again, they are interchangeable. We're going to have our 2 pi over t, because that's our omega naught. Our omega naught is just 2 pi over t. And then we are going to have a t, or then dt. And so if we again look at the notes linked below the like button on a little bit, this is in section 16.1. It's just basic, again, differential equation stuff, but we have a integration table. And we can use this because we have this t cosine 2 pi over t part that we need to look at. We are going to set all of this stuff as a, and then we're going to solve for it. So let's factor out the constants again. We're going to have 4 times 50, that's going to yield us 200, times 10 to the 6th. We are then going to have t and then pi. And then inside of here, we are going to start. So we have 1 over a squared, so we can just flip our a entirely. We're going to have t squared divided by 4 pi times n, and this is all squared. And this is being multiplied by the cosine of our n 2 pi little t over our big T, which is representative as the period. And then we can do plus. We just have our a here, so we're going to do t divided by n 2 pi. And then we have times our little t sine of our a, which is just n 2 pi, and then times t. Then we have over t. And this is going from 0 to t over 2. We can simplify this a little bit. Let's take out the t's first. So this t, this is going to become t to the 1, and this t down here is out. Now we can simplify these 2's. So this 2, this will become a 2, and this will just become 100. Now, from here, we can start plugging our bounds in, right? So we'll rewrite this. We'll have 100 times 10 to the 6th over pi. And, well, t over 2, we're plugging this in for our cosine. So the 2 over t is going to cancel out. We're just being left with a cosine n times pi. And so this is going to give us, and we can write this out, cosine n pi, but it's being multiplied by t over pi n squared. Remember, don't forget this first part. And so we're just going to have cosine n times pi inside of here. And then if we plug it into sine, well, it's just going to be sine n pi. We know sine times anything times pi is just 0. So we don't need to include that. I'll just include a plus 0 for that. And then we have to minus our next bound, right? So let's plug in 0 for the cosine part. Everything inside of our cosine is going to 0 out. Cosine of 0 is just 1. And so we are going to have our t over the, oh, I realized that I forgot this 2 earlier. We should have a 2 right here. 2 pi n squared. And then if we plug 0 into whatever we have sine, 0 out, sine of 0 is just 0. So we're going to have a plus 0. And so this is what we're going to have. And now what we can do is simplify this a little bit. We can factor out everything. For the t over 2 pi n squared, we can factor that out. So we're going to have 100 times 10 to the 6th divided by pi. And then we're going to have t, and then we're going to have 2, and then pi n squared. And then inside of here, we're going to have cosine n pi minus 1. Oh, sorry, this should have a parenthesis around that, not around the whole thing. So this is what we're going to have. This t, we know the period is 2 pi times 10 to the negative 6th. So the 10 to the negative 6's will cancel out. The 2 pi is going to cancel out with these. And we're just left with a 100 over pi n squared cosine n pi minus 1. Now, we can go even a little further with this, right? So let's just write this out right here. We have 100 pi n squared, and then we have our cosine n pi minus 1. And if we plug in a positive number to our n, or I'm sorry, if we plug in an even number to an n, like 2, 4, 6, 8, something like that, we're going to get cosine even number times pi. This is going to yield us a 1. That means we'll have a 1 minus 1. So everything is going to 0 out. So we can write for even, it equals to 0. Now, for odd, if we plug an odd number in here, we're going to get cosine of an odd number times pi. This is going to give us a negative 1, so we have negative 1 minus 1. And so this is going to yield us a negative 200, because we're going to have a 2 inside here. We're going to have a negative 2 inside of here. Negative 200 over pi n squared. And this is what we're going to want to focus on. So this is what we're saving here, and we're going to save this with our AV. Now, for our b of n, we don't need to find it here because it is even. In the notes linked below the like button, it shows us that b of n does not need to be found if we have even symmetry, because b of n is just 0. So we can say that b of n is equal to 0. We're not going to be using it for this specific waveform. And so that's it for the first part. We're going to come back to this when we write it in Fourier series. So I'm kind of putting a pause on the part 1, but now we're going to look at part 2 when we look at the transfer function for this. Now, to make a transfer function, we're going to need to use the node voltage method for this entire part. We know that voltage across here and across here is the same, so we're going to just call it V0. However, we do need to combine these two impedances. We know that we need to convert to the S domain. This was covered previously. So to convert to the S domain, our ZL is going to be equal to S times L. Our capacitor is just going to be ZC is equal to 1 over SC. We have a capacitor and a resistor in parallel, so we need to use the parallel form to combine them. We're going to say that our R naught is equal to this. We're going to have one R naught over our first impedance, so it's going to be 1 over SC, and we can just rewrite this as SC. And then from here, we are going to have plus our next impedance, which is 1 over the resistor, raised to the negative first power. Now, if we simplify this, everything, we're going to have R over 1 plus SCR. And so this is going to be equation for our R naught, and now we can plug it into the node voltage method. Node voltage method says, oh, and also, by the way, transfer function. We want it to get it into h of s, right? So h of s is equal to v naught over our v input, which would be vg here. So node voltage method, we have v naught is equal to our vg, and then inside of here, we have our first part. So we're going to have our R naught plus, and then the 20 millihenry inductor, which we'll just call S of L right here. And the R naught is equivalent, or it's tied to whatever voltage we have out here. So if we had an input voltage, it would be the 20 millihenry inductor. So now looking at this, what we can do is simplify. We notice that we have this all in the denominator, and we don't want that all in the denominator. So what we're going to do is multiply both the top and bottom by 1 plus SCR. And so this is going to give us that our V naught is equal to VG, and then this is equal to, well, we will just have an R up top if we do this, and then right here we'll just have an R plus, and now we're multiplying the SL by the 1 plus SCR, right? So we're going to have a SL plus S squared L CR. And so this is going to be our equation. Now, we want this in J omega, right? Since we have a wave, it's going to be J omega n. And when we do this, it's super important to just remember that we're converting to the imaginary form, J omega, so that we can convert it into the polar form. Because when we look at the polar form, we can use it to combine with our Fourier series. So that's what we're going for. We need to put it in the polar form. So Vm naught is equal to Vg, or R right here. Now we can plug in our values. When we plug in our values, we have this 20 kilo ohm resistor. So V naught is equal to Vg, and then, oh, there shouldn't be a equals, there should be multiplication here. We're going to have 20 times 10 cubed. Then we know we have 20 times 10 cubed on the bottom here, plus we are going to have our inductor, which is 20 times 10 to the negative cubed because of the millihenries. So 20 times 10 to the negative cubed times our S plus. Now we have our inductor, our capacitor, and our resistor, which is 20 millihenries, 50 picofarads, and then 20 kilo ohms, right? We can plug all of this into a calculator, and then if we do so, we are going to get that we have a 2 times 10 to the negative 8 with our S squared. Now, rule, we want to get our S squared by itself. And to get our S squared by itself, what we can just do is, well, there's two things that we can do, and I'm going to do them separately. First, I'm going to divide everything by 2. So this is going to become a 1, this is going to become a 10, this is going to become a 10, and this is going to become a 10. Now, I'm going to multiply the top and bottom by 10 to the 8th, and that's going to simplify. So that's going to give us a V naught is equal to Vg, and then this is being multiplied by, if we combine everything up top together, we are just going to have a 10 to the 12th. On the bottom, we're going to have a 10 to the 12th. We're going to have a plus 10 to the 6th times S plus our S squared. So this is what we have. Now, we need to convert this into the J omega n domain, right? Because that's what I said. We're basically going to set our S equal to J omega n. And our omega we know is 2 pi over the t, over the period, right? Well, our period, 2 pi, is e times 10 to the negative 6. That's our period, right? We wrote this out earlier. 2 pi times 10 to the negative 6. Well, if we have 2 pi over 2 pi times 10 to the negative 6, this is just going to give us 10 to the 6th. So our omega is just 10 to the 6th. So we can write this as Jn 10 to the 6th. Okay, and now we're going to plug this in for all of our S's. So this is going to give us that our V naught is equal to Vg, and then we have 10 to the 12th, 10 to the 12th. We are going to have a plus we're combining our 10 to the 6s. This is going to give us a 10 to the 12th. We're going to have j times n. Next, we have a plus s squared. Well, we have a j in here, right? A j being squared it's an imaginary number, right? So it's I, an imaginary number. We have an imaginary number squared. And so our imaginary number being squared is going to give us a -1 whenever we have that. So we have minus our 10 to the 6th squared is just 10 to the 12th. And then we're going to have an n squared. And so we can see here that our 10 to the 12ths are just going to cancel out because it's in all of them. So that's what we're going to get. We're going to have a v0 is equal to vg, and then this is being multiplied by a 1 plus j times n minus n squared. So this is going to be our equation. Now we need to find our Vrms. And our Vrms, it's going to help if we look at all of this, right, what we've done so far. So we have our AV, we have our AN, which we found right here. And now we found our V0, VG. Now these all look separate, but they're going to come in really handy. And this is what we're doing in step number 3, right? So we've done all of this so far. Now we need to put it together. I'll just do it in super simple kind of a way that can be replicated for any problem. What we're going to do for here, we need to first make a Fourier series. And a Fourier series looks something like this. So this is going to help us with the first part that we did. When we look at this V of g right here, what we're plugging in is all of this. So what that means, and also if we had a B of n, by the way, we would also need to plug it in as well, but we don't have a B of n. Just have an A of n here. So that means when we combine this equation and this equation, we are going to get that our V0, which is what we want to find, because remember power is basically V times I, voltage times current. We're going to get V0 is equal to, we're going to plug in our A of n, right? That's what we want to plug in. We don't need to worry about the sign or the cosine right here because we don't have it right here. We're only solving for the odds because our evens are 0. So we're going to have a -200 over pi times n. And remember, pi n is squared, right? And then this is being multiplied by a 1. And then we have I kind of read this out of order, but jn minus n squared plus 1. Now, it's important that we don't forget that we need our summation as well. So we're going to go from infinity like this, and we're starting at n is equal to 1. So this is going to be what we're looking at. This is our V0, and it's going to help us find our Vrms. So now we need to find our Vrms. That is going to be step 3. And the formula, before we go any further, to find power, we're going to say that power is equal to our V times our I. We don't have I here. We're basing this off the 20 kilo ohm resistor. Remember, it's asked for that in the problem. So instead of I, we're going to use Ohm's law and just say that we're going to have voltage over resistance. And so we can rewrite this as our Vrms squared over our resistance, right? We know our resistance is 20 kilo ohms, so 20k, that's 10 cubed. Now we need to find our Vrms. Well, our Vrms is going to be equal to, and this is, by the way, V0 RMS. That is what we want to find. The reason we want to find V0 RMS is because we have the V0 over this resistor. That's important to note. We want to find the voltage over the resistor because that's what the power that's dealing with it. And this is equal to, we have the square root of our AV squared plus our next value. We're just doing an approximation here, so we're going to have a couple different values in here. We are going to have our A1 divided by the square root of 2 squared plus our A3 over square root of 2 squared. And we're going to do this for, like I said, a couple different values. If we had our B of n, this would contribute to this. That'll be shown in the next video in the playlist link below the like button. But for now, we are just going to do our A of n because we only have A in here. But again, the next example will include B of n. So we're going to have A of n, A of 1, A of 3, A of 5, and then we will also have an a of 7. And so what we need to do is continuously go through our ends and then plug them in here, right? And remember that this is over the square root of 2 and all of it's being squared. The actual equation can be found in the notes linked below the like button, but it's basically saying that we have V naught RMS, or VRMS, right? Because the naught is special for this case. We're going to have the square root of our AV squared plus the summation of our n is equal to 1. And then inside of here, we have our a of n over square root of 2 squared. So we can reference that if we ever get lost. Our AV is 25 here. So we are going to have 25 squared plus. Now let's look at the first one. So this is when our AN is 1. We're going to take all of this and plug it into a calculator. Since we're using imaginary numbers, I like to use Symbol Lab. So we're going to come over here. This is our equation. The I represents the J. I'm going to plug a 1 in here instead of a 3, but we just have a 1 like this. And so that's going to give us this equation, 200i pi over 2. And now we need to convert this into polar form because this is currently in the rectangular form. Whenever we have imaginary numbers, we're in the rectangular form. So to convert from rectangular to polar, we would need to first get the magnitude. That would be plugging it in here. Our real number is 0, and then our imaginary number is this value. And so if we click go, we're just going to get a 200. Oh, by the way, we should not include the imaginary number in here. We don't need the imaginary number, just the value in front of it. And this is going to give us this other decimal, 20.26423. Now, for our tangent, we would plug in our imaginary number over our real number. We can't plug in 0 because we can't divide by 0, so we're going to plug in something super close to 0. We have an angle of 90 degrees. Now, we're only concerned about the magnitude here. We don't need to worry about the angle when we're plugging it into here. Again, we do not need to worry about the angle, but it is important to know how to find it. So we're just going to use the magnitude. We are going to have our a of 1 be 20.26 over the square root of 2, and this is all squared. And that is from the VRMS formula. It can be found in the notes. So, but it is also to the right over here. That's what we're plugging it into. Now we have to do this again for our A3. We're not doing it for our even numbers because, as I said over here, they all equal to 0. So we can't really use them in our approximation because they won't turn out as a good approximation. So we're going to change this value from 1 to 3 for all of these that we need to change it to. I'll click go here. And then this is going to be what we're given. Now we're going to take these values, we're going to plug them into our square root. And then once we do that, we should get a 0.26352 over our, well, we're just going to get the first part, but we need to put it over a square root of 2 and square it. And that's going to be for our A3. Now, we need to do the same thing for our A5 and our A7. You can just do that yourself. You just repeatedly plug it into the calculator. You just change the ends. And this should give us a 0.03306 over square root of 2. And this is going to be squared plus. Now, the next thing is our A of 7. And our A7 is 0.26352 divided by the square root of 2. And this is all squared. So lots of numbers. But remember, again, you're just basically plugging in the values here, right? You're not here, in here. And then you're going to take these and you're going to plug them into here to find the magnitude. We've gone over that many times in previous problems. And so we should be good with the rectangular to polar conversion now. And so now we have our VRMS. And now that we have our VRMS, we can just plug it into our P. If we were to plug all of this into the calculator, everything underneath the square root, we would get that our V naught RMS is equal to 28.81 approximately. So we're going to plug in 28.81 squared, and then we're going to have the 20 kilo ohms on the bottom. And then after we do that, we're going to convert this to milli. So we just need to multiply it by 1 milli over 10 to the negative cubed. Or if you wanted to, you can do the math, but basically just don't include this K down here and you would get the milliwatt conversion of it from kilo to milliwatt. So this, if we plug this into a calculator, is going to equal 41.6 approximately. And so let's reveal the answer. We can see that it is indeed 41.6. And that's how you go about solving this problem. you would first make the Fourier series for it. So everything we did in this first part, come down here, make our Fourier series. For this problem specifically, steady state, all that stuff, we're going to have to do a part 2 where we find the h of s, the transfer function, right? And then we're going to need to plug it in here, make this V naught equation. So this is the V naught, the voltage over this resistor. And then we're going to use it in part 3. And part 3 is where we state that our P is this, we want to find this, and that makes us find our VRMS, right? And that is what our V naught is. So we're basically finding our V naught, but the RMS of our V naught. And when we look at RMS, this is the function for it. If we were using current, it would be the same thing. It would just be I naught RMS. And so that is how we would go about solving this problem. And that is all of its work entirely.